All right. Looks like everyone's gotten in. So again, welcome to tonight's webinar, Exploring Earth's Superpowers, Understanding Our Climate and How We Can Protect It. Um, I'm John Lohr with Science Olympiad. Excited you guys could join us. And I was just telling our presenters that they're helping me fulfill kind of a long-term goal I've had because as part of Science Olympiad, we've been working with the National Oceanographic and Atmospheric Administration for uh, almost a decade that I've been aware of. And one of my things was I always wanted to connect to the National Weather Service to help and talk about our meteorology event. So we're actually able to do that. And I will tell you that I've had the good fortune to attend a couple of National Weather Service presentations, and they've always been fantastic. So, not to put too much pressure on our speakers tonight, Mikal Montgomery and Steve LaVoie, but I think it's going to be a fantastic session. So, real quickly on some of the basics, yes, this session is going to be recorded. You will be getting a link to the recording sometime tomorrow afternoon. Then we will also be posting it on our Science Olympiad YouTube channel. So you'll be able to find it. Also, if you have questions, go ahead and use the question and answer feature. It's kind of in the middle of the toolbar for Zoom, and it's to like just off center to the right side as you're looking at the screen. So please feel free to put your questions in there. If you run into any problems, you have any, you're not sure about like technical things, like, hey, I just lost sound or something. Is that us? Is that you? Feel free to put those comments in the chat. And that's to the left side of center in the toolbar. But then, so with having shared all of that, without further ado, I'm going to turn it over to Mikal Montgomery and Steve LaVoie from the National Weather Service. Thank you very much for being here, gentlemen.
All right. Thanks so
Yes,
much,
thank you
John.
for having us.
Yeah, thank you. Thank you so much. So, welcome, good evening or afternoon, depending on where you're tuning in from. My name's Steve LaVoie, and I'm a meteorologist with the National Weather Service Forecast Office in Columbia, South Carolina. So the current time on the East Coast is 6:03 p.m. And so I've been with the National Weather Service as a meteorologist for 3.5 years now.
All right. Hello, all. I am Mikal Montgomery. I work at the National Weather Service office in Hanford, California. I am sometimes a meteorologist, sometimes data collector, sometimes other things, but I've been working here at the Weather Service for about a year and a half and excited to talk to you all about climate.
All right. And to start us all off, so as John mentioned, we are underneath the National Atmospheric and Oceanic Administration, or NOAA for short. And within there lies the National Weather Service, which we have a variety of offices all across the country. We have 122 weather forecast offices. So that's where you can see the buildings where we are in right now. And so I am in the lower right. So that is my building here at the Columbia Metropolitan Airport in West Columbia, South Carolina. And Mikal is over there in Hanford, the Hanford office, Hanford, California. So we are coming coast to coast for you this evening/afternoon. And of course, it's not just meteorologists that work for NOAA and the National Weather Service. We need all kinds of kinds. So not only that, but even in an individual weather forecast office, we have electronics technicians who maintain our radar and other important computer equipment. We have an information technology officer who's working more on the back end, the programming, the computer programming. We have administrative assistants who pay the bills, all the support staff who keep the office running. And in addition, we have other offices such as the Opal and our hydrologist as well. So lots of different avenues that you can take here in the National Weather Service. And I think Mikal can speak on that specifically on his role in the Weather Service.
Yeah, so, my position is the Opal, so Observation Program Leader. So basically what that means is I go out and collect a lot of data in the field, so a lot of atmospheric data in national parks, different areas, people's houses sometimes, who help us out with our climate network. So a lot of the stuff that I collect and a lot of information I collect is for climatology, that I send back to Asheville, North Carolina, and we're able to look at all of this climate data.
Yes, thank you for that. And so that is just, again, one of those support staffs that is at every office, or, when they're fully staffed. We actually have an opening over here for an opal. And I am a meteorologist. So my typical jobs include forecasting the weather out to 7 days. That goes onto our website, weather.gov. And as needed, I'll issue specialized watches, warnings, and advisories. And that is our primary duty, is to protect life and property. And of course, advance, the nation's economy, the commerce. So what's the difference between climate and weather? So my wheelhouse is, of course, meteorology. And so I study the weather. That is going to be short changes in our atmosphere. So again, we're talking minutes to hours to days. And it occurs at a specific time and place. So what we're talking about are like definitive numbers. So when we say the high temperature in Columbia on Sunday will be 57 degrees, we're talking about the weather. These are actual terms. By comparison, we're talking about climate. That's going to be an average. So it's accumulated weather over a very long period of time. And that'll be the focus of today's presentation. So we won't be talking much about the weather itself, but how that Earth's climate has changed. And of course, we're going to talk about months, years, decades, and even millennia. And so when we're talking about climate, we're talking about averages. And so it does change slowly over a course of many years. It's more regional and long-term. So we could say that the average high temperature in Columbia, South Carolina on December 15th is 65 degrees. That's talking about the climate. So that's when we average all that weather on that day over a long period of time, that's what we get. So climate is what you expect. Weather is what you get. That is a very good way to remember. Like, we're expecting certain conditions on a certain time of year, but the weather can change. It can be much hotter or colder on a given day. So for example, we're going to reference Chicago, Illinois, and this is what your climate normals look like in the city of Chicago. I know you guys are joining us from all across the country. And so you can see this time of year, Chicago is on a downward trend. It's, of course, winter in the northern hemisphere where we are located. And so temperatures are going to probably bottom out somewhere in mid-January, in this case, in Chicago. Looks like the average temperature is quite cold in Chicago. Looks like about 25 degrees, and then it starts to warm up as we head through our late winter, spring, and comes to a peak somewhere around mid-July. Looks like their normal is about 75 degrees. So quite a variant in the climate in Chicago. So it's what we call a four seasons climate, where you have your winter, spring, summer, fall. And as we'll talk about, not everyone has four distinct seasons. And there's certain climates where it's not temperature that dictates the seasons. It's actually whether it's wet or dry. Now, if we take a look at, by comparison, this is what Chicago has actually recorded. So this is the weather showing up on the blue bars versus the brown, which is your normal climate. So you can see that there was a time early this year that Chicago was particularly cold. And so it looks like in the middle of January there, it was a very cold period. And otherwise it was just a lot of up and down. And effectively we see that with the weather, is that you're going to have periods where it's a little bit warmer than average. We'll have a storm go by, the temperature will drop and then gradually recover. And it all depends again on the overall weather pattern. So the weather mostly falls within within the brown, but you can see there are periods where it was hotter and colder than usual. So, and of course, we won't open it up, but just kind of think in your head whether this is weather or climate. So when we say it snowed 3 inches yesterday, do you think that's weather or climate? And that would be a case of weather. Next up, typically rainfall in June is over 1 inch. Climate. The forecast high temperature for tomorrow is 97 degrees. Well, that is a great example of a weather forecast. And finally, the winter should be colder than normal. And that is actually going to be a climate forecast. So let's dive into climate. I know that one of the things you'll be covering in the Olympiad is climate zones. So we're going to talk all about the various climate zones that exist, particularly in the United States, but we'll touch on the whole planet. And so these are the climate zones for the United States. And so we're going to touch on the 5 main categories, and there are subcategories. For example, if you're in Chicago, you have a different climate than you do here in South Carolina, than Mikal has over in California. And so we'll go into all the nitty gritty of that. And so there are 22 climate regions, so areas that have very similar types of climates. We kind of group them together. And so that's across the United States, Alaska, Hawaii, and Puerto Rico, and of course the territories. The 5 major climate types are A, tropical, B, arid, C, temperate, D, continental, and E, polar. And what's interesting to note is that the climate in Columbia and the climate in Hanford are both considered temperate climate, C. But as we'll talk about, it's a very different type of climate between South Carolina and California. But first, we'll talk about tropical climate zones. And so you could go to a tropical climate zone if you went to Hawaii or Florida, South Florida specifically, or any of our outlying territories like Puerto Rico and the Virgin Islands. And these are characterized by climates that have very high temperatures. So the year-round average is going to be about 64 degrees or higher, very warm parts of the world. And the majority of the A climate zones are actually very close to Earth's equator. And the reason behind that is that at the equator, you get the same amount of heating roughly all through the year. They don't really have seasonal climates when it comes to temperature. However, there are different sub-variants of the tropical climate zones that have well-defined wet and dry seasons. And so if you're in the dark blue on screen, that is tropical rainforest. And so these climates don't have a defined wet or dry season. They're just hot and they're wet all year round. So a tiny little bit of Florida comes up in that. A good chunk of Hawaii and Puerto Rico are that tropical rainforest. Tropical monsoon is kind of a transition zone where they do have some drier months and at least 1 month with less than 2.4 inches of precipitation. And so you can see as you go from Fort Lauderdale to Miami and then down to Key West, Florida, you're going to see that we have more, we transition from one type to another. And so Key West is actually considered the tropical savanna, light blue. And so if you're in a tropical savanna, you're still hot all year round, but you have a more defined wet and dry season. So the climate at Key West, for example, if you were there, you would know that it was a little bit drier this time of year. Usually from about October to May is a drier season because their rain comes more from the tropics. And the tropics in our part of the world are more active during what we call hurricane season. So from June to November is where most of the rain in Key West falls. But if you go a little bit further north to like Fort Lauderdale or Palm Beach, those locations are close enough to where we get winter rains to make it that far south more often. And so this is what Miami looks like. Remember, they're in that kind of transitionary zone. And you can see that again, you see May through October, they have more rain. They have about 3 inches of rain or greater on every month. And then they have a couple of drier months. In fact, February is the driest month in Miami. So this is a climate graph. And so the red line represents your monthly temperature. And so you can see in January, the temperature looks to be about 70 degrees. It only warms up to about 82 in the summer. So there's not a large variance in temperature in Miami. It's just fairly warm all year round. So for example, this would be a great place if you wanted to go someplace warm for Christmas. You'd probably be almost guaranteed to have nice warm weather if you went to Miami. And in fact, it would be on the drier side, but it's not particularly like a couple inches of rain every month. That's not too bad. It's dry for Miami, but it wouldn't be dry in a place like Phoenix, which we'll cover next. And so next up are B, arid climate zones. And in the United States, a lot of the Western United States away from the Pacific coast would be in the B class. And so this one's a little bit harder to define. Basically, we say that the evaporation and transpiration that occurs at these locations exceeds annual precipitation, which again, you can just think these are very dry locations. And so they're broken down into 4 different categories. You've got hot deserts in red. You've got cold deserts in pink. Hot semi-arid is that dark color, which is pretty much exclusive to Texas and Arizona. And then that kind of peach light orange color, which most of the map that you see is in that color, is cold semi-arid. And so the biggest difference between these two is that you'll find the hot deserts and hot semi-arid are going to be closer to the equator, but not always near the equator. There's always exceptions. But the farther away you go, you're going to be more into the what we would consider the cold deserts. In fact, there are many deserts that it does snow. Some of the precipitation that falls will be frozen. And so, for example, Boise, Idaho, it can snow in Boise. And so that's an example of a cold semi-arid location. And this is Phoenix, Arizona. So this is their graph. And what you'll notice is that their temperatures do vary. So they actually have I would say a warm and then a very hot season, because if you look at January, you're having an average high temperature of say 52 degrees versus looks like July is 95 degrees. So it goes from being warm to downright hot. And Phoenix, if you're not familiar, often has many days where the temperature is over 100 degrees. And you can also notice that they do have a wet and dry season. And so the spring in Phoenix is particularly dry. In fact, June, it looks like they might have about 1/10 of an inch of precipitation, where they do have a wet season in coming up right now in the winter, where they can have, an inch or two. And now if we go back to make a note here that Phoenix's wettest month, that would be February, about 1.5 inches. Let's jump back to Miami. Their driest month was right about there, 1.5 inches. So in Miami, their driest month of the year is actually the wettest month in Phoenix. And it just so happens that it's in February. Now, C is kind of the most varied climate zone. A lot of different climates, as you can see from the map, get lumped in together into what's called the temperate climate zone. And so what we're going to do is talk about kind of the subcategories within type C, because again, the United States has a lot of zones in the C category. First up would be what we would call Mediterranean. So that's going to be your yellows and your dark yellows. So Mikal in Hanford is in a temperate climate zone, just like me, but they're more Mediterranean hot summer. And so that's the comparison there, is that the characteristics are a little bit different. If you know of the Mediterranean Sea over in Europe, so that's the type of climate they're used to. The temperatures don't vary. Again, once you move inland, it's a little bit different, but it's particularly along the coast. There's not much variation in temperature through the year. And then they typically kind of have that wet and dry type of season. Next up would be oceanic, which you can see occurs in a couple states, particularly southeastern Alaska. There's a large island in mainland Alaska down there on the southeastern part of the state. And then also parts of Washington state have an oceanic type of climate. And then finally, my climate zone is called humid subtropical. And that's a large chunk of the United States. So it goes from places like Austin, Texas, all the way to the coast, including Florida, South the Carolinas, all the way up to even New York City is considered humid subtropical. So we do have a year-round 4 seasons climate. It doesn't get as cold here as it does in Chicago, and snow is very rare for us in particular. But we are considered that climate, that humid subtropical zone with a hot summer. So if you were in the C climate zone, you can see that the average monthly temperatures are between 50 degrees or higher in the warm season, and usually above 27 degrees in the cold season. So Chicago is pretty close between zone C and D, for example, but they have some colder months than, say, Southern Illinois, which is why they're currently in the D category. And again, there's a very large variation. We don't have time to go all into the nitty gritty, but you can think of C as a temperate zone. So mostly between about 30 degrees north and south and 45 degrees north and south is where you'll find your temperate zones across the world. And we'll show a climate map of the entire planet. And there's a lot of factors that go into why the zones are where they are. So San Francisco, California is in, again, that C category. And this is a place that you can see has a well-defined wet and dry season. Again, the wintertime is their wettest, where they typically see between in January and February, even December, between it looks like 3.9 and probably 4.5 inches of precipitation. And their temperatures vary from about 49 degrees in January to about maybe 63, 64, it looks like in October. And so not much variation in temperature, but well-defined wet and dry seasons. Now, Charlotte, which is close to where I am, you can see much different. So precipitation, we don't really have well-defined wet or dry seasons. It's about the same every month, nothing too extreme. But we do have a larger variant in temperature. So our winter temperature in January is about 41 degrees in Charlotte, and then it goes all the way up to about 80 degrees in the summer. And so where I am in Columbia, it's a little bit warmer, but very similar climate. Now we're going to go on to the next one up, which is continental climate. And so you'll see a lot of this from about 40 to 45 degrees north and south to about 60 degrees north and south. And so now we're moving further and further away from the equator. And now we have much different, there's a high differential in day length. And so obviously up here in the D climate zones, you have very long days in the summer and shorter days in the winter. And it's a lot more defined, even more extreme than down here in the south, depending on how far north you're going. And so again, there's a lot of subtypes in the D group. And so the two main ones are humid continental. And that's what you have across the northern United States. So that's a huge area from Kansas City north to the Canadian border. And then you take that east all the way into New England. So places like Boston and Portland, Maine. And then there's subarctic, which in our country is mainly Alaska. A large portion of the state of Alaska is considered subarctic. So it's a D group, but it's a different type of D group versus what we have in the Northeast. And so we characterize a D climate zone by the average temperature of 50 degrees or greater in the warmest month. So it's a little bit different than C, and an average temperature of less than 27 degrees in the coldest month. And so again, that's why Chicago falls into that D group. And then depending on where you are, you can have a great variance in temperature and precipitation patterns outside of that definition. And here's Chicago. Again, we can see that much like what you saw with Charlotte, there's not a really well-defined wet or dry season. You can see it maybe a little bit wetter in the spring, a little bit drier in the winter. And then they have an even greater variance in their temperatures. So they go from very cold, below freezing in the winter as the average high temperature, all the way up to about, looks like 75 degrees in the summer is the average. And then the last group we're going to talk about are E zones, a lot easier. So we're going back down to pretty keep it simple kind of deal. And the E is the polar climate zone. So this is usually about 60 degrees north and south of the equator, and then obviously all the way out to the poles. And the tundra category is colored in light gray. And in the United States, this is exclusive to far northern Alaska. That's the one spot where you'll get a polar type of climate zone. And you can't find it in the United States, but there's also the ice cap climate zone, which for the ice cap, they say that the year-round temperatures are below freezing. So we're talking mostly Greenland, the North Pole, and Antarctica. And this is what Barrow, Alaska looks like. So you can see that Barrow does have a few months where temperatures do get above freezing on average. That's why it's not an ice cap zone. And they do have a well-defined wet season here. Overall, it's fairly dry, but you can see in July and August, they do have more rainfall. And it's also much warmer, relatively speaking. As you can see, their winter, it looks like the average in January is about 23 degrees below zero in Fahrenheit. And then it only gets above to about, looks like 10 below in Fahrenheit, 23 in Celsius, and about 41 degrees Fahrenheit in the summer. So climate zones of the world. So when we go back to Chicago, specifically, they have a humid continental climate with a hot summer. And so other cities that have a similar climate to Chicago would be Montreal, Quebec in Canada, Nagano, Japan, Odessa, Ukraine. And so those three are kind of the more notable cities within the same climate as Chicago. So if you were to move to one of those locations, you'd experience very similar conditions. And what's unique about that climate is that you can't find it in the southern hemisphere. And so the reason why the climates are a bit different, if you look between North America, Europe, and Asia versus Africa, South America, and Australia, is that there's more water in the southern hemisphere versus land. And so that impacts the different types of climates. So latitude plays a big role. The amount of water available determines the climate. And then, of course, how far you are away from a large body of water, such as an ocean. And so there's no DFA climates in South America, Africa, Australia, or Antarctica. But there are D climates. They're just a little bit more limited and different types. And so that's a quick rundown of climate. I'm going to switch over to here. Looks like we don't have any questions. There is something in the chat. I want to just double check. Let's see. Do you expect climate zones to shift over time as temperatures increase globally, sea level rise, etc.? Kayla, that is an excellent question. And so we are definitely going to cover that in the next few slides. So stay tuned for that. And but in the interim, we're going to go back over to what climate change is, which will answer that question. And so what is climate change? There's a couple of words that get used interchangeably, climate change and global warming. Back in the late 20th century, we started to see that the planet was warming. We saw these trends coming. And so that was the original term. And so the observation was that the whole planet was warming, and we're going to see impacts because of that warming. Well, over time, we realized that, yes, overall the planet's warming, but there's areas that are also getting cooler. There's areas that are getting drier, areas that are getting warmer. So the appropriate term that we like to use is global climate change, or climate change for short. And again, that's to cover all the changes that are going on and not just the large scale warming. And so a little bit of Earth's history, going back to the last ice age, effectively, that was roughly 2.6 million years ago to 11,000 years ago. And so what happened was our climate was shifting pretty rapidly during that period. And there were periods where we had a lot of ice sheets. The ice sheets actually expanded, as you can see, well across most of Canada was encased in thick ice. And even a large portion of North America, much of that current D climate. So your D and E climates were all pushed further south. And what was notable about this is that sea levels dropped because a lot of Earth's water was stuck in this ice. And as a result, there was actually a land bridge at one point between North America and Asia. And it has been theorized that a lot of folks, we know that humanity began in Africa, and we believe a lot of humans actually crossed this land bridge during the last ice age. They would have been more of the transient populations, and they would have followed the food across the land bridge into Alaska. And we think this might be one of the ways that peoples began to populate North America, because the Americas originally didn't have any humans. They were all in Africa and then spread out to other locations. Newer theories actually do suggest some may have come by boat as well. They probably would have followed the coastline down into North America. So a couple ways that we got into North America. So when the glaciers started to retreat, which group of lakes were created in North America? And the answer is the Great Lakes. And so as the ice sheet was retreating, it actually did leave behind very large lakes, all sorts of different features that we can't get into. But the largest and most notable feature are, of course, the Great Lakes that we have on the border between the US and Canada. Now, speeding things up, we're going to go to the last 2,000-ish years of history on Earth. And this is the global average temperature. Excuse me. And what you can notice here is that the global average temperature, from what we can tell, was, there were some swings, but it was fairly stable from at least the year 0 CE to about 900. Then we started seeing a decrease in global temperatures from about 900 to 1000 CE to approximately 1700 CE. And so that is what's going on overall on the planet, but we're going to talk about some regional climate changes. And so there was something called the medieval warm period, and that was from roughly 950 to 1250 CE. And so this is where overall things were much warmer across Europe, and we also believe portions of North America. And civilization started to flourish. The Vikings in particular were known for exploring beyond Europe. And we know that they settled in Iceland, Greenland, and they even had temporary settlements in parts of Canada. Now, what's interesting is, even though the temperature was warming regionally, overall, remember, global temperatures were cooling during the medieval warm period. And then over time, we saw that in Europe, the temperature started cooling from about 1300 to 1850 CE. The glaciers returned. And in fact, that picture there, that artist painting, is there used to be Christmas celebrations on the River Thames in London. And so the ice was so thick, you could put people, you could put tents on there, and there used to be a celebration there for decades. Of course, now you don't see the River Thames freeze over like that because it's a much warmer climate. Now, on the not so happy side, we had colder and wetter seasons leading to crop failure. So the Irish potato famine is an example of widespread potato blight caused by these conditions. And so we had a lot of folks leaving Europe. This was the age of exploration. And so global temperatures were still cooling till about 1700, and then they started coming back up. But then there was a dramatic cooling around 1800. And in the year 1800, and just before that, there were a lot of revolutions. And so the climate actually had a part of a role in that, in the American Revolution, the French Revolution, and other periods of unsettled unrest during that time in Europe and North America. And in particular, the year 1816 was known as the year without a summer, or 1800 and froze to death. This is likely the coldest year experienced in the last 200 years. And it was primarily caused by the eruption of Mount Tambora in 1815. And so when volcanoes erupt, they release a bunch of chemicals and gases up into our atmosphere, and that can impact the climate. And you can see that Tambora was the largest eruption that we've had in recent history. Krakatoa in 1883 influenced the climate, as did another eruption in 1991, but it was much more regional in nature. This had significant impacts on particularly the northeastern United States and Western Europe. Now, after that, we noticed that we started to see a gradual warming. And this is where we start talking about climate change and where humans play a role. Because all of a sudden, we started pumping a bunch of greenhouse gases into our atmosphere. And so it was only a gradual warming, though, after 1816. So it wasn't going to be too much noticeable at that point. And that's because we started building factories, but they were more regional, the Eastern United States, Western Europe. But then there was a sudden warming in the late 19th and 20th century, and then a dramatic warming since World War II, 1945. Why would that be? Well, you can see in orange, that was the warming during the first industrial revolution, where factories started getting built. And then the second industrial revolution. So that was the late 19th century and early 20th century. That was a new period where trains became available. We were rapidly increasing our technology. And so more and more communities became more industrialized. And so the industry expanded to places like Germany, Italy, the Western United States. And so, yes, we saw a more dramatic warming during that period. And then after World War I and World War II, a lot of countries became more industrialized. A lot of former colonies across the planet started doing the same thing. They had their own industrial revolution. And we just had more and more technology. And so that's why we started seeing this sudden warming, because more and more greenhouse gases were coming out. Cars, every single car is producing greenhouse gases. Well, the ones that aren't electric, fully electric, of course. So we just have more cars, more factories, more people. And so we need to do something to help mitigate that. And that is where I'm going to turn it over to my partner here to talk about how we measure the change in climate and what we plan to do with it.
All right. Thank you, Steve. I'm going to share my screen. All right. Hopefully everyone is able to see this. Steve, can I get a confirmation?
Good to go.
Awesome. Awesome. So Steve, talked about a lot about history and um, what climate looks like, what climate change looks like, and the things that we're looking at. But exactly how do we measure climate change? So we measure climate change by taking observations and using different instruments. So one of the biggest things that scientists look at are ice cores. So basically that distant look into the past and what exactly the climate looked like in the past, much like tree rings, if you're all familiar with that. We also have our own global climate network, which I work for, and we have over 7,000 sites here in the continental US, Puerto Rico, Guam, and Alaska. We compare different climate models. So we have a climate prediction center that looks at all of these different models and figures out exactly what the next time frames are going to look like. So what the seasons are going to look like, what the next few months are going to look like, and you look at those here in the now and in the past to figure out what the future is going to look like. We also have satellites. And then lastly, we have surface observation systems like the ones that you may see at the airport or, at your local weather station. So moving over into the global atmospheric circulations. So whenever we think about weather, we think about the movement of thermals and the movement of systems. So high and low pressure systems. So we look at polar, Ferrel, and Hadley cells. And we're going to start off with the Hadley cell, which is a low latitude. Air moves towards the equator where it's heated and rises vertically. So it's pushing towards the equator, and we kind of get from the Hadley cell, we get a lot of those tropical systems, and the reason why there's so much precipitation along the equator is because of the Hadley cells. For the Ferrel cell, that's a little bit further north, closer to the mid latitudes and closer to the polar cell, but it's where air flows poleward and eastward. So we're looking at it flowing more to the north, so bringing that warmer air up north. And then lastly, we have the polar cell, which has the polar easterlies that bring that cold air down to the mid latitudes. So moving over to ocean currents. So warm ocean currents flow away from the equator and towards the poles. So when you think about the Gulf streams and such, all of those that flow is moving towards the poles and bringing up that warmer temperature. And this is something that we're studying because we're starting to see that those Gulf streams and those warmer current ocean currents are actually moving further closer to the poles over the years. So I think it's about an average of 1 to 2 miles per year, which may not seem like much, but in a long grand scheme of things, it is quite a bit. Cold currents flow away from the poles and towards the equator. And then lastly, counter currents flow opposite of wind currents to fill those gaps in between. One of the things that we talk about a lot as meteorologists is, La Nina or El Nino. So, what is the indicator of what the winter is going to look like, for example. So this is the La Nina winter. So with the La Nina winter, you're seeing sea surface temperatures cool in the central and eastern Pacific. So what La Nina basically is looking at is essentially where the jet stream is located. So where that variable polar jet stream is located. And for the La Nina winter, it's further north. So although you're going to see wetter temperatures, it's going to be a lot colder further north and not further south. You're going to see wetter areas in the Pacific Northwest and the northern Midwest areas, the Great Lakes. But closer to Mexico and the southern U.S., it's going to be a lot drier. And then for El Nino, there's two jet streams. So there's three jet streams that dominate the Earth. So you have the Arctic jet stream, you have the polar jet stream, and then you have the subtropical jet, which you can see in red down south. Um, for El Nino, the jet stream is the polar jet stream moves a lot further north, and you have warmer temperatures that start to move over the northern US as well as Alaska. And then that subtropical jet moves closer to the US from the Caribbean, and it brings up a lot of moisture and a lot of warmer air to that southern part of the US. However, in the close to the Midwest, there's a lot of drier air in that area. So, what exactly is causing this climate change? So, first thing to talk about is greenhouse gas effect. So, we all know that the sun's radiation travels towards the earth. But how much of that is emitted and how much of it is pushed back into the atmosphere? So about half of it is reflected or absorbed by the clouds in the atmosphere. So that sun radiation is pushing, and it's half of it is making it to the earth and the other half is getting reflected and absorbed by the clouds into the atmosphere. Um, the earth also releases its own heat back towards space. So not only is it taking in that heat from the in that radiation from the sun, but it also pushes it back out. And then some of that heat passes directly through the atmosphere. So it may push through clouds, thinner clouds, so more of ice and cirrus clouds that are higher. But if it's thicker clouds or like stratus or cumulus clouds, it may not be able to pass through directly, which it'll bounce back more towards the Earth's surface. But most of it is captured and retained by greenhouse gases. So on a normal CO2 emissions with greenhouse effect, um, we're still getting those effects and that climate change effect, but it's a lot less, and there's a lot less heat trapped in the atmosphere, allowing more heat to escape into space. But once you increase that CO2, and there's an abundance of it with cars and such, um, you're going to see more greenhouse gases. Therefore, there's going to be more heat trapped in the atmosphere and just hotter temperatures for us here on the surface. So we see that greenhouse gases are increasing, and mostly that's carbon dioxide, and that's from the human element and the human factors. Although we also see nitrous oxide increasing, methane increasing, and then fluorinated gases also increasing. So, like I said on the last slide, carbon dioxide is contributing the most. So that's 79%. Um, and a lot of this is from non-electric cars and from us as human beings, um, helping to increase this carbon dioxide emission. But methane at 11%, nitrous oxide at 7%, and fluorinated gases at 3% are also huge factors into this. But a lot of this is coming from transportation, electricity generation, and industry. So, with the rest being agriculture, commercial, and residential. So, looking over 800,000 years, and Steve kind of touched on this a little bit, but we've gone through different phases and periods where we'll see less carbon dioxide and it'll trend up, but it'll come back down, trend up, come back down. And this was all before cars. But as we've gotten closer to the year that we're currently in and the present time frame, um, we're seeing that increase is exponential and it's going up rapidly. So the highest carbon dioxide has been during all of human civilization. So why is carbon dioxide increasing so much? Well, because of human activity. And you can see that on this chart. The red line, which is the human activity, is very similar to the orange line, which is all of the activity across the board. And the human activity is the main driver in this increase in carbon dioxide. And that trend has significantly gone up since about that World War II timeframe, and it just looks to continue to keep on increasing. So here's the proof of human influence. So this is the carbon dioxide emissions and atmospheric concentration from 1750 to 2020. So CO2 in the atmosphere and the emissions are on the same path. And you can see that path grow rapidly since the World War II era. And, it really has no sign of stoppage. Um, it- the emissions rose slowly, probably about 5 billion tons a year in the mid 20th century, before skyrocketing to more than 35 billion tons per year by the end of the century. So if CO2 emissions continue like it is today, you know, in the atmosphere is projected to exceed 900 parts per million by the end of this century. So currently it's at 412, and the impacts of 412 are very much seen and felt by all of us. But if there's 900 parts per million by the end of the century, that is very, very significant and something that is being studied on a daily basis. So what are some signs of, climate change? So there are 11 signs of a warming world that we monitor for. That's the Arctic sea ice, which is decreasing rapidly. Sea surface temperature, which is very much increasing, and that's something that we've seen significantly and something that has impacted the hurricane season, our past hurricane season, very significantly. Air temperature over the ocean heat content, which goes back to those currents that I was talking about. Humidity is increasing, global sea temperatures are increasing, snow is decreasing, and that goes into the variability of the seasons and what winters are looking like these days. So there's warmer winters than ever before in some areas, so that means there's less snow to be seen. Air temperature over land is increasing, temperature over the lower atmosphere is increasing, and then our glaciers are also decreasing. So, going back to the surface temperatures of the globe, they are increasing. And you can see that on this chart that the difference from 1901 to 2000 average in 2020 and on, um, it went from cooler, so a lot cooler areas, to a lot warmer. And that's something that we're seeing continuously going on and a trend that is going to continue unless, we make changes on our own. So this shows a 5-year average of departure from the long-term average of global surface temperatures. So 1884, there was a lot cooler of 5-year average time frame, but then in the year 2020, over that 5 years, we saw a lot of areas that are warming, especially further up north, where there's a lot more glaciers and polar ice caps. And with something like that, and those areas warming in particular, you're going to see a higher sea level rise and a lot faster than normal. So, for the average temperature trend in Illinois, um, it looks when you look at this, you can see that there's the high highs and then there's the low lows. But the blue line will show you that there is that trend across the board. So it may not seem like much, but that trend slowly going up is going to continuously show itself over the years. And this is 2023, but by 2050, who knows where that may be at that point? And then so on and so forth. As these temperatures increase, things happen exponentially. So, Great Lakes ice. One of the things that I've been talking about is the polar ice caps and ice coverage. And over the years, the Great Lakes has been one area that we've looked at significantly. And during the winter months, as you can see, January through April, the 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 ice coverage is where it's been at, exactly where it needs to be in the past. However, recently, um, 2024 to date, there's been a lot less ice coverage. And you can see that with the trend on the right, um, in the right graph, that we've been declining every single year. And we're slowly on that declining trend. But that declining trend will eventually get to where it's zero at certain times of the year. And that's something that we definitely can't have. So, rising global upper ocean heat content. So, this is basically just talks about, where was the heat compared to average during these years, the heat in the ocean. So, in the 60s and 70s, it was below average on for heat. But as the years have gone on since then, you've seen above average heat content in the oceans throughout globally. And with that being said, that also leads to that glacier and that ice melting, but it also enhances some of the natural disasters that we do see here as meteorologists. So once again, less snow cover and glaciers. So for a lot of areas, we don't expect too much spring snow coverage. However, the areas that we do study, we've seen a lot less spring snow coverage since about the year 1990. And then from 2010 and on, there's been a lot less. So that, that has declined significantly. And then as far as the glacier mass balance, so the glacier mass balance is how thick a glacier is, and that has also been decreasing and allowing the water to increase. So water levels increasing. And for sea level rises, that kind of ties hand in hand with the last slide that you know we have gone up and trended up over the years for the global sea level. And looking at satellite, it shows definitely there's areas that haven't had water on their coasts, but now they're starting to see more water pushed towards their coasts. And that is something that is continuously going up for the years. So, what does the future look like? So for a future temperature change, we have projected annual global carbon emissions and then projected global temperatures. So for the carbon emissions, there's several scenarios. The higher scenario is the worst case, and that's with RCP 8.5. But then for the projected global temperatures associated with that, with the worst case at the RCP 8.5, it is 8 to 10 degree increase globally. 8 to 10 degrees globally is quite a bit when you talk about the scale and where exactly the temperatures are going to increase. But the lower scenario is RCP of 2.6, which would only increase our temperatures to about 2 to 4 degrees. So it's about 2.5 degrees. And that's kind of what we want. That's the best base case scenario. And then the future sea level rises go hand in hand with that last slide. So with RCP increasing, um, the future sea level rise could be in that extreme zone, which is 2.5 meters. But uh, with the lowest and the one that we actually are looking for will be low, and that's only about zero point 0.2 meters. So for the possible impacts of climate change, like I was talking about, we have the increased extreme weather, which we have seen this past year with hurricanes. We have more variability in winter recreation, so there might be a lot less snow in a lot areas, loss of coastal living areas, and that's with an increase in the sea level temperatures, or with the increase in the water, sea water, so pushing closer to the coasts and kind of overtaking those areas on the coast. For agriculture, we have more variability in growing conditions, longer growing seasons, and the impact of crop yields. More heat stress to people and animals, so a lot hotter in certain places, in places that wouldn't expect and don't normally see. A lot hotter temperatures, those increase, and then increased evaporation. So for us here, a little plug. Taking weather observations. I take weather observations for my job here, but we also have a network of CocoRAs that you can also take weather observations from your home, from a business, and such. And all of this data comes back to us to use to study weather, water, and climate. And for the tools and resources, so if you want to look all this information up and do your own research, you can go to climate.gov and you can see all of these things. So spring snow, mountain glaciers, Arctic sea ice, whatever you want associated with climate, we do have that on climate.gov. And there's also the climate resilience toolkit, which is toolkit.climate.gov. So if you need to figure out, or you want to figure out exactly how, what precautions to take with climate resilience, you can go to this website. And that concludes our presentation. We are ready for any questions that you may have.
Thank you very much, guys. If anyone has any questions, feel free to throw them in the Q&A. We got time for maybe one or two. All right. While people think, I'm going to do a couple of little housekeeping things. Some questions that were asked in the chat was seeing if the guys would be willing to share their slides, and we got a definite answer of yes. So not only will you be getting the recording, but we'll also make sure you have access to the slides. Somebody also asked if they could get copies of what has been going on in the Q&A, because there's been a lot of great questions and a lot of great answers put there. Yes, I think I'll be able to get those downloaded, and we'll make sure if I can get those out of the system, you will definitely get access to them as well. And looks like we have two questions here. One looks like I'm going to end up taking. The other one from Barbara, I'm going to throw to Steve and Mikal. It says, does regenerative farming help make agriculture more climate friendly? And if it does, how does it do it?
Well, I would say that I would go with leaning towards yes, especially if it's done on a larger scale. What it can do is, again, the more plants we have, we can actually draw carbon dioxide outside of our atmosphere and store it within the soil and the plants. So if the soil's more healthy and being, refreshed, regenerated, and we see that type of pattern, we can do that on a much larger scale, not just local to one farm, or another, then yeah, absolutely over time, we could see, again, more carbon dioxide being pulled from the atmosphere. It can definitely help. Just even more trees in general would be very beneficial. If we continue, I know we have to get rid of trees, we have to chop trees down, but if we replace them, that's what's very important. We need to make sure we have sustainable logging practices as well.
All right. No, it's a great piece. And the last two in here are really, I think I'm going to tackle them because it seems to be focused more on the event itself. They're trying to find out what are the expectations and how can they create effective tests for the students. And I think the expectations, I mean, obviously you want to take a look at the rules for the event. And that will identify the kind of the content and some of the levels that you can look at. The other thing to help set with expectations, there are a couple of items in the Science Olympiad store related to meteorology that are example tests and past exams on the topic and samples that kind of give you an idea of, I guess, important points and kind of ways to look at the questions. The other thing I will tell you is I want to thank the guys because the slides and the detail and the information they shared, I think that also can help you set kind of what the expectations and kind of points to what important content the kids need to know. The other thing I would encourage you to check out is on our Science Olympiad website, so soinc.org, under the Division B events and particularly the meteorology page, there are new resources up there from NOAA that our partners have been working on and putting together that I think will also help you understand kind of what the parameters of the event are a little bit better. And then last but not least, two big things to help. One, you'll see them on the webpage when the meteorology page when they become available, and that are release tests from invitationals. So when invitationals share their exams with us, we will put them up on the webpage. The other thing that I would encourage you to do with your team is take the team to an invitational tournament. And there are almost 400 of them that happen every season. Now, some of them can involve travel, but there are also a good number of them that have online options. So all you would need to do is go to the school to take a test. And the cool thing about invitationals, they give you all the resources from the event. So you'll get to see the test, you'll get to see your answers, you'll get the answer key. You take all that stuff with you as a team, and that can be another great way to kind of figure out what's the right level, right target for your kids. So hopefully that helps you. I would just ask those of you that are still with us, if you guys could say a thank you to Steve and Mikal. That, Steve stayed late at work. Mikal carved some time out of his day to spend some time with us. So thank you very much, guys. It's greatly appreciated. I also want to wish everybody the best, not only for your Science Olympiad season, but I hope everybody has a wonderful holiday season as well. If you're still looking for resources and content, I will put in a plug next Thursday. We will have our final webinar of 2024, and it'll be looking at crime busters and forensics. So if anybody is looking for help with crime busters and forensics, there's still time to sign up for next week's webinar on next Thursday. So again, gentlemen, thank you so much. Your time and knowledge and everything is greatly appreciated by everybody. So I hope you both have a wonderful evening and have a wonderful holidays.
Thank you so much. Thanks everyone for attending. Have a great evening, and happy holidays for everyone.